We're going to continue our discussion of chirality with a topic called optical rotation. We use optical rotation to test our mixtures of enantiomers to see how pure they are. We've learned that lessons in medicine, hard lessons, that it's very important to know the optical activity or the purity of your chiral molecules before you administer a drug. The most illustrative example was the thalidomide story back in the late 50s, early 60s. They had the cure for, a cure for morning sickness, which is, ladies when they're pregnant, later, some ladies all the way through the pregnancy, they feel nauseous and sick all the time. It's terrible. And they had thalidomide, and it worked. But what they didn't know is only one enantiomer was helping the ladies with those side effects of pregnancy, and the other enantiomer fit perfectly as an inhibitor in an enzyme that was responsible for blood vessel growth. And it stops that enzyme from being able to do its job. So new limbs were starting to grow for the baby. In the third trimester is when things are really growing. You see mommy go from here to here. It's a big change, right? So that's when you need the most blood vessel growth. And if you don't have the blood vessel growth, the limbs will stop growing. So we had thousands of babies worldwide grown with little flippers for arms and legs. And it was a terrible time in history because we didn't know this lesson that we had to learn. You have to test each enantiomer separately when you're testing drugs now. And either one enantiomer is beneficial and the other is innocuous, which means it doesn't hurt. You can sell that drug combination. Or both enantiomers are beneficial. You can sell that drug combination. But you cannot sell a combination with a lethal drug with a beneficial drug together. So one solution to that problem would be only sell the one isomer that works, that causes a benefit, right? We didn't know at the time that with thalidomide, that wasn't even an option that would have saved the solved the problem. Because sometimes in biochemistry, there are enzymes that will convert one hand to another, like take an R and make it S. They flip it. They break a bond off and put it on the other side, literally. That's how it happens. Okay? And thalidomide is one of those stereocenters where the stereocenter is next to a carbonyl. And in biochemistry, those can always be flipped from R to S using enzymes that are already in you and me. Okay? So that wouldn't have been the solution. Thalidomide is not the answer for morning sickness ever, because your body takes the harmful, the good one, and makes some of it into the hurtful one, the inhibitor. So long story short, we need to be able to test in the lab how much of each isomer we have. We need to know exactly how much of each isomer we have, right? And that's when we use something called optical purity, which takes advantage of a property that chiral molecules have. They take a special light called plane polarized light. You can create plane polarized light yourself. You can go buy some very expensive sunglasses called polarizing lenses and shine a light through it. And almost all the light gets blocked. Very little gets through. They're really good sunglasses. They block most of the sunlight. And only one plane of light goes through. You know light travels in waves, right? Maybe you don't. You don't really need to know for this course, but I'm telling you they travel in waves. And it's not just that wave. There'll be this wave, 90 degrees and 60 degrees. All versions of that wave, different rotations of it, okay? That's normal light. The filter takes every plane except one and just blocks it. And it lets one plane go through. Now that light that went through is called plane polarized light because it's only one plane. And a chiral molecule, if you have it in a solution where that light's coming through, will rotate the light either in a positive direction or a negative direction. depending on which enantiomer you have. And a property of enantiomers is this. So say the R enantiomer rotated light negative 15 degrees. Guess what the S enantiomer is going to rotate light? Positive 15 degrees, exactly. So that's a property of enantiomers. They rotate plane polarized light the same amount, but opposite direction. Okay? This molecule rotates light when it's this enantiomer in a negative direction, and the other one is positive 150. I just called this molecule X. It's in a category of molecules that I really like in chapter 5 called terpenes. So you'll see that molecule about 3 times on this test. And it was fall 15, but I changed it. It's no longer the fall 15 question. I made it, the numbers work better because we have no calculators here. We have to know a lot of things before we start. So I think the first activity is just going to be watching me define things, and then we'll solve the problem. First thing we're going to define is what is this in the box, and that's the reference value from literature. Okay? You have to be given that for this question. And what the square bracket means is, you guys think it might mean molarity? Square just means standard conditions. And I will outline what standard conditions are. Here they are. Concentration equals 1 gram per milliliter. I know it looks like density, doesn't it? But it's a gram of solute. That's the thing dissolved. Here, molecule X, and it's an enantiomer. And the volume of the solution, milliliters. L is the path length of light. And what are the units? dm, what do they stand for? We don't use those units very much in science, but these people that do these experiments, that's their favorite unit for this. What does it stand for, dm? That gives a capital D. And that would be 10 meters, but this is not that. Other direction, decimeter, 1/10 of a meter, right? We don't use decis too much in this country. Okay, and temperature equals 20 degrees C. And that just needs to match that. We don't use temperature in our calculations, but they should match. That's a standard lab temperature, like a room temperature. Most labs are close to 20 degrees. This room's probably 21 right now. My thermometer, I don't even know. Okay. So the thing we need to know is how to standardize a lab value. That's alpha observed. I'm going to get rid of the parentheses. Okay, so here is the standard lab value. OBS stands for observed. OBS, observed. Okay, the standard is equal to the normal lab value times C times, divided by C times L. That's how you standardize. And I'm going to prove that to you in a second. alpha observed times C times L equals lab value observed. That's not that. I mean, everybody in the room should be able to do that. That was just math, right? Multiply both sides by C times L. So before I go about solving this problem, we're going to talk. I got a question for you. What would the observed lab value be if I had all these conditions the same, except I changed concentration to 2 grams per milliliter? I'd like to point out, this is the reference value under standard conditions, negative 150. If I keep everything standard except double this one, what do you think is going to happen to the alpha observed right here? It'll be double. That's what this equation says. If the value of C is double, then the alpha observed would be double. Right? You can say the same for length. If you doubled it to 2 decimeters, you would double it. You get negative 300. If I doubled both, negative 600. That's quadruple factor, right? Double, double is quadruple. So you'd be multiplying this by 4, which is negative 150 times 4 is negative 600. And the easy question is, what is the alpha D20, standard alpha D20 for the enantiomer of molecule X? You already answered this question, but not the specific one. So what is the answer? Positive 150. That's all you need to know. Now, one more thing you need to know. What would be the alpha observed? What is alpha observed for any 50-50 mix of enantiomers? By the way, that's called a racemic solution. So when I ask what's a racemic solution, you say a 50-50 mix of both enantiomers. Right? So what's the answer? 0. Nice answer. 0 degrees. You have as many molecules rotating this direction as you do this one. They cancel each other, right? Same reason a meso molecule has no rotation. It's not chiral. It doesn't rotate light. You've got as many R's as S's in the same molecule, right? Canceling each other. I think we're ready to maybe answer the question. All right, this would be the introductory video. And ending.